When we introduced this course a couple of weeks back, I made us to understand that finite element methods or finite element analysis is a general numerical method for solving partial differentials. And we looked at several things. Time will not permit me to go through all what, if you have not been in this lecture for some time, all what you have lost because you are not here. But because you will get the lecture materials, I believe you'll be able to catch up. If there are any questions during the review class, we will be looking at them. But that is if you indicate that you are in this lecture by going to the chat box and typing. If you can hear me, type 11 on the chat box. If you can hear me, type 11 on the chat box. If you can hear me, type 11 on the chat box. Does it mean these 3 persons here you cannot hear? Your microphones are not even enabled. If your microphone is not enabled, go to the chat box and type. You can type in the chat box. All right, we had an introduction to stress analysis. We looked at the basic concepts of finite element method or finite analysis. We looked at 1-dimension, 2-dimension, and 3-dimensional elements. We also analyzed linear statics, where is an analysis where linear relation holds between applied forces and displacements. In this slide, we looked at linear static analysis, what it contains, and the area of coverage. We looked at linear elasticity assumption, which is the relationship between loads and deformation, which must be linear. We looked at static load assumption, which states that all acting loads must be time independent. And we finally understood that minor deformation assumption is stating that the deformation will not be less than 0.2%. And I ended up with some assignments, which if you have attended other classes, you will see. The next time we met, we looked at energy methods, where we said that these methods that are based on linear elastic behavior and conservation of energy, that is, the work done by external forces always equals to the energy stored in the structure under load. And these concepts made us to look at work, potential energy, kinetic energy, according to Bernoulli and Lagrange. In this level you are, I'm very sure that you must have gone through your 100 and 200 level, because this is a 300 level course. You must have known about work, must have known about potential energy and kinetic energy. So we looked about variation principles. We looked on variation principles, the principles of variational situations. And we studied what quadrature is. The quadrature rule is an approximation of the definite integral of a function, and is usually stated as a weighted sum of functions, values at specific points within the domain of integration. This is the formula for calculating quadrature, where n is a positive integer. The capital letter N is always the small letter n plus 1, which is called the Newton-Cotes quadrature formula. In triangulation, which is also referred as parallax technique, it is a method of measuring distance indirectly by creating an imaginary triangle between an observer and an object whose distance is to be estimated. This is the same method that astronomers use to measure the distances of heavenly or celestial bodies. Now, there is a principle called energy minimization, and it is one of the backbones of finite element methods or finite element analysis. Let me simplify what principle of energy minimization is. And whenever a particular boundary condition is applied on a given body or material, it leads to a number of configurations that may prove to be a disadvantage for the same condition. Therefore, to figure out the appropriate configuration of the substance, we use FEM to be able to study it by using the process of energy minimization. And what is the principle of energy minimization? It says that whenever a boundary condition like a displacement or force is applied on the material for a number of reasons, the configuration of the body takes the minimum energy and thus gives the appropriate reading of the geometrical flaws. And that was where Galician's method was birthed, which I encourage us to read more about the Galician's method. Today, we're going to be looking at affine mapping, which we started the last time. Affine mapping from a reference element. Generally, mapping is all about knowing where an object is imaginarily by plotting coordinates. And there is a local mapping, there is a global mapping. First of all, let us understand what coordinate systems are. Coordinate systems are generally either Cartesian, orthogonal, or right-handed. And the purpose is to quantitatively define the position of a particular point or rigid body. That is all about mapping. Now, a reference system, a local coordinate system, is a reference system within the larger reference system. The LCS, which is when you elaborate, is the local coordinate system, as opposed to the global coordinate system, GCS. The LCS is within the GCS. Now, the LCS is a reference system that is within the global coordinate system, which is the GCS. Number two, this system holds its own origin and axis, which are attached to the body in question. Also, the LCS must define a specific point on or within the body. It must also define the orientation to the global system. That means you must be able to define an object by the LCS in relationship with the GCS. The origin and orientation, which is equal to the secondary frame of reference, or the LCS. Now, these are all the conditions characteristics of the local coordinate system. Now, the global coordinate system, which of course we have mentioned before, is the GCS, is based on the tilting of the Earth's surface into cells. Each cell has a local Cartesian frame of reference. Positions in the GCS are specified by 4 coordinates, X, Y, Z, and the cell ID. You can see the diagram there. Each positioning is characterized by 4 coordinates. These coordinates, or these coordinates, like I've said, is the X, the Y, the Z, and the cell ID.